Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and today we're diving into a technology that's been the stuff of science fiction for over a century, but is finally coming into our daily lives. Wireless power transfer. Imagine never needing to plug in your phone, laptop, or electric vehicle. Power simply appears wherever you need it. No cords, no bulky chargers, no hunting for outlets. Sounds like magic, but it's science, and engineers are making it real. Every day we rely on wires and cords. Our phones, laptops, kitchen appliances, even our cars are tethered by cords that limit where we can place them, how we design them, and how convenient they really are. Wireless power promises to cut those cords without sacrificing energy or safety. From charging your smartwatch while you sleep, to powering fleets of electric vehicles in garages automatically, this technology has the potential to transform how we live, work, and move. In this episode, we'll explore the fascinating science behind wireless power, how energy can jump from one coil to another without physical contact, the clever tricks that engineers use to make it efficient, and the different methods, from inductive charging to far-field energy beaming. We'll also look at companies racing to commercialize the technology, the real-world applications already here, and the challenges that still stand in the way. By the end of the episode, you'll understand how wireless power works, why it's capturing the imagination of engineers and tech enthusiasts alike, and how it could change the devices and vehicles you rely on every single day. Get ready to see engineering and energy in a whole new way, untethered and invisible, yet all around you. Wireless power transfer, or WPT, is the process of transmitting electrical energy from a power source to an electrical load without the use of wires. Although it might seem futuristic, the principles behind WPT have been studied for over a century, and they are rooted in well-understood laws of physics. At its core, wireless power relies on the interaction of electric and magnetic fields, which are forces created by moving magnets. Electricity as we know it is the flow of electrons, negatively charged subatomic particles, through a conductive material like a wire. In conventional wired systems, electrons move through the wire to carry energy to devices. Wireless power, however, uses fields instead of wires to influence electrons remotely. These fields can transmit energy across short or even long distances, depending on the method used. One of the foundational methods, and the most basic, is inductive coupling. In inductive systems, a transmitter coil, a loop of conductive wire connected to an alternating current, or AC source, generates a changing magnetic field. According to the laws of electromagnetism, changing magnetic field creates a voltage in a nearby conductor. This induced voltage drives a current in the receiver coil, which powers the device. The closer and more precisely aligned the coils are, the higher the efficiency of energy transfer. To understand why this works, consider the idea of magnetic flux, a measure of how much a magnetic field passes through a surface. Transmitter coil creates a fluctuating magnetic flux that passes through the receiver coil. The faster the flux changes, the greater the induced voltage in the receiver coil, and therefore the greater the amount the device charges. Engineers carefully link and design the number of coils, the coil diameter, and the frequency of the alternating current to minimize flux linkage and energy transfer. Maximize. A step beyond simple induction is resonant inductive coupling, also called magnetic resonance. In this approach, both the transmitter and receiver coils are tuned to oscillate at the same natural frequency, a phenomenon called resonance. When a system resonates, even a small input can create large oscillations, like pushing a swing at exactly the right moment to make the person on the swing higher and higher. Resonance allows energy to bounce efficiently between coils, increasing the distance over which power can be transferred, sometimes from centimeters to several meters. Resonant systems also reduce energy lost as heat or stray electromagnetic radiation, making them more efficient than standard inductive setups. Another wireless power transfer method is far-field energy transfer, which uses electromagnetic waves such as radio waves, microwaves, or laser beams. In these systems, a transmitter converts energy into a wave that moves through space, or through the air, to a receiver. The receiver, also called a rectenna, and this is a combination of an antenna and a rectifier, converts the wave's energy back into electricity that a receiving device can use. Far field transfer allows longer distance power delivery, but is less efficient due to wave dispersion, which spreads the energy over a larger area and makes the technology less energy efficient. Engineers often use beamforming, technology where multiple antennas shape and focus the wave energy toward the receiver to reduce the effect that wave dispersion has and increase efficiency. Efficiency in all wireless power systems, regardless of type, depends heavily on impedance matching, a concept from electrical engineering that describes how much circuit resists alternating current. If the transmitter and receiver impedances are not properly matched, much of the energy reflects back instead of being absorbed. Engineers use capacitors, inductors, and precise circuit design to align impedances, ensuring energy is efficiently transferred rather than wasted. Materials science also plays a critical role in wireless power. Transmitter and receiver coils are commonly made from high conductivity metals, like copper or silver, which allow electrons to move freely with minimal resistance. Adding ferrite cores, magnetic materials that guide magnetic fields, concentrates the field in the coils, reducing energy loss and improving efficiency. Researchers are experimenting with metamaterials, artificially structured materials that manipulate electromagnetic fields in ways conventional materials cannot. Metamaterials could possibly focus fields, reduce interference, and even allow wireless power transfer to devices that are misaligned or far away. Temperature, alignment, and distance also affect system performance. In inductive and resonant systems, the efficiency drops sharply as the coils move apart or become misaligned. Far-field systems lose energy as waves spread out, meaning precise targeting or multiple transmitters might be required. Engineers mitigate these effects using real-time feedback systems, where the receiver communicates the position and orientation to the transmitter, allowing dynamic adjustments in field strength and frequency. Safety is another, probably more important consideration. Strong electromagnetic fields can interfere with electronic devices, medical implants, or even living tissue. Regulatory agencies, such as the FCC, limit the field strength for consumer devices. Modern wireless charging systems typically operate at very low power levels to minimize health risks, reduce interference, and prevent overheating. Wireless power transfer also involves complex energy conversion processes. The transmitter converts DC electricity into AC to create the magnetic field. The field that moves through space induces a current in the receiver coil, and then the receiver converts AC back into DC in the device. Each step involves a potential energy loss, which engineers must minimize using advanced circuit designs, high-quality materials, and thermal management techniques. In cutting-edge applications, scientists are exploring multi-coil networks to simultaneously charge multiple devices or direct energy to mobile routes or drones in motion. Some systems use adaptive resonance tuning, dynamically adjusting the resonant frequency to maintain high efficiency as the receiver moves. Others incorporate wireless feedback protocols, allowing devices to request more or less power depending on the battery state, environmental conditions, or safety limits. Finally, the integration of smart electronics into wireless power systems makes them not only convenient, but highly efficient. Communication between transmitter and receiver allows for precise control of voltage, current, and timing. This coordination prevents overheating, optimizes charging speed, and reduces energy waste, ensuring devices receive the correct amount of power safely and efficiently. Now that we've explored the basics of how WPT works, let's peel back another layer and look at the engineering details. These are the details that make the leap from cool science idea to technology that can actually power and revolutionize phones and cars. Don't worry, we'll keep it clear and easy to follow. But by the end of this section, you'll see how much clever engineering has done to make something as simple as placing your phone on a charging pad actually work. First, we'll start with the circuits that make it possible. When you plug a wireless charger into the wall, the electricity it receives is direct current, or DC, after it's converted by the charger's power supply. But wireless charging needs alternating current, or AC, because only AC creates the changing magnetic fields that allow power to jump from one coil to another. To make this AC, the transmitter uses special electronic switches called MOSFETs. You can think of a MOSFET as a super fast light switch. Instead of flicking on and off once per second like a normal light switch, a MOSFET can flip thousands or even millions of times per second. These rapid flips create the high-frequency signals that drive the transmitting coil. Now here's where things get really clever. Resonance tuning. If you've ever pushed someone on a swing, you know that timing is everything. Push at the right moment and the swing soars with almost no effort. Push at the wrong time and it barely moves. Wireless power works in the same way. Engineers design the coils and tiny energy storing components, called capacitors, so the transmitter and receiver swing in the same natural rhythm. When both are in sync, energy flows much more smoothly and efficiently between them. But here's the tricky part. The conditions keep changing as devices move around or tilt. So engineers have to build circuits that constantly adjust to this rhythm in real time, making sure the energy flows at peak efficiency no matter what. But even with resonance, not all the energy makes it through. Some is lost as heat in the wires or as stray electromagnetic fields. One of the biggest culprits is resistance, the tendency of wires to heat up when current flows. At the high frequencies used in wireless power, this problem gets worse because of something called the skin effect. Imagine water in a pipe that only flows around the edges and ignores the middle. It's basically what happens to electrons at high speeds. To fight this, engineers need to use specially braided wires made of many thin strands, called Litz wire. This design spreads the current more evenly and keeps things cooler, reducing energy wasted as heat. They also tend to add ferrite materials, which are magnetic ceramics, to guide the magnetic field right where it's needed and prevent energy from leaking away. Shaping these magnetic fields is another art form. If you've ever adjusted the beam of a flashlight, you know you could make it wide and soft or narrow and focused, like when sending power across a room to a drone or robot. Researchers are even experimenting with metamaterials, engineered substances that can bend fields in unusual ways, almost like giving magnets a lens that can direct and shape these magnetic fields so that, just like your flashlight, they can either be soft and wide or narrow and focused. This can help specifically shape the magnetic field for specific applications and specific uses. Finally, let's talk about communication. Wireless power systems don't just blast energy blindly, they're also talking to the devices that they charge. Your phone, for example, can signal back, saying, "I'm here, I need this much power, and by the way, my battery's almost full, so you can slow down." This two-way conversation keeps everything safe, prevents overheating, and makes charging smarter. That's why you've probably noticed your phone charging quickly at first, and then slowing down near the end. It's not a flaw, it's deliberate communication to protect the battery and save energy. So while wireless power might look simple, just a pad in a phone with no cord, under the surface is a carefully tuned orchestra of high-speed switches, resonant timing, special wires, magnetic materials, field-shaping tricks, and even digital conversations between devices. Each part plays a role in turning invisible fields into real usable electricity. And as engineers continue to refine these details, the efficiency, range, and practicality of wireless power will only improve. As evidence of this, wireless power has come a long way from the early experiments of Nikola Tesla to the practical systems we see today. The most common method currently in use is inductive coupling. You've likely encountered this already through things like wireless phone chargers, electric toothbrushes, and even some smartwatches. The energy transfer works over very short distances, usually the maximum of a few centimeters, but it provides a reliable and a convenient way to power devices without cords. The technology is precise enough that engineers have optimized coil designs and electromagnetic shielding to reduce energy loss and prevent interference with other electronics, to the point where it's mass producible and mass sellable. In the automotive world, wireless charging is gaining traction as a real alternative to plugging in an electric vehicle. Porsche, for example, has demonstrated an 11 kilowatt wireless inductive charging system for one of its new 2026 electric cars. This system includes a floor unit that transmits power from the car's onboard receiver when the vehicle is properly aligned, assisted by visual guidance from the car's surround view parking display. This setup allows for automatic charging as soon as the vehicle is positioned correctly and is intended primarily for home use, since most electrical vehicle charging happens in private garages. Although the system is large, heavy, and requires professional installation, it showcases how far wireless power technology has come and how far it has matured to handle high-demand applications like vehicle charging. Similarly, consumer electronics are beginning to incorporate wireless power in new ways. Midea, a Chinese appliance company, has introduced the Celestial Flex series, which includes kitchen devices such as blenders and kettles that can operate when placed on a specifically designed, compatible induction plates. By eliminating costs and cords, These devices make everyday tasks more convenient and show how wireless power can move beyond mobile electronics into larger appliances. Looking forward, resonant inductive coupling is the next breakthrough scientists are working toward creating effective and efficient. It could reshape the way we interact with energy daily. In transportation, cars, buses, and delivery vehicles could charge automatically without cables, reducing wear on connectors and simplifying infrastructure. In urban environments, streetlights, sensors, and public transportation could be powered without excessive wiring, making smart cities more feasible and flexible. For portable or remote devices, such as drones and environmental sensors, wireless power offers the potential to operate continuously without the interruption of battery swaps or manual recharging. Perhaps the most ambitious vision involves space-based solar power, where satellites collect sunlight in orbit and beam it to Earth using electromagnetic waves. While this idea remains largely conceptual, advances in far-field wireless power technologies, such as energy transmission via microwave or laser beams, make it incredibly possible that one day we could harvest and transmit energy from space to anywhere on Earth. In short, wireless power transfer has evolved from a curiosity into a field with real-world applications and extraordinary potential. Advances in resonant coupling, material science, and smart control systems are pushing the limits of efficiency and range, while practical implementations in vehicles, appliances, and devices are demonstrating its value today. As research continues, the technology may soon transform how we think about energy delivery, moving cords from our lives, enabling new device designs, and making it possible to power everything from our phones to entire cities with invisible, reliable energy. Of course, as exciting as this all sounds, wireless power isn't without trade-offs. One of the biggest is efficiency. Moving energy without wires is almost always more wasteful than sending it directly through a conductor, which means more electricity has to be generated to get the same usable output. On a small scale, like charging a phone, that might not matter much, but scaled up to fleets of cars or entire neighborhoods, those losses could add up to higher energy demands and more strain on the grid. Engineers are working hard to minimize these losses, yet the physics of transmission will always set some limits. There are also environmental and ethical considerations. Materials like copper, silver, and ferrite metals are essential to building coils and circuits efficiently, but mining and processing them can carry real ecological costs. And while space-based solar power or long-range energy beaming might sound revolutionary, directing high-power electromagnetic waves through the atmosphere raises concerns about safety, interference, and even weaponization if misused. Regulatory agencies keep tight controls on field strength and frequency, but the more ambitious the applications become, the more oversight and international cooperation that they will require. Ultimately, wireless power promises a future that feels cleaner and more seamless, but realizing that future responsibility means balancing convenience with sustainability. Engineers and policymakers will need to weigh efficiency, resource use, and public safety alongside innovation, making sure the technology grows in a way that truly benefits both people and the planet. As we've seen, wireless power transfer isn't just a futuristic idea. It's a technology rooted in real physics, clever engineering, and advanced material science. From the way magnetic fields can jump between coils, to resonance that allows energy to flow more efficiently over distance, the science behind wireless power is as elegant as it is powerful. Engineers have overcome countless challenges to make this work safely, efficiently, and reliably. Whether it's charging your phone while it rests on a pad, powering medical devices without ever needing a cord, or even envisioning electric cars that charge themselves automatically as they park. But the journey doesn't stop here. There are still technological hurdles, environmental considerations, and ethical questions to navigate, from energy efficiency to safety to resource use and long-term sustainability. Yet, the potential is enormous. We could have cities where streetlights, sensors, and public transport are powered invisibly, drones that could fly indefinitely without battery swaps, even the potential of beaming solar energy from space to Earth. Wireless power has the potential to reshape how we live, work, and move, removing cords, unlocking new designs, and transforming energy from something we plug in to something we interact with seamlessly. Ultimately, wireless power is more than a convenience. It's a glimpse into the future where energy is invisible, accessible, and integrated into the very fabric of our world. The science is real, the applications are growing, and the possibilities are almost limitless. This is Energy Untethered, and it's just getting started.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.